K. So we have had a lot of like chapters dedicated to K and the equilibrium constant there. We've had Ka, Kb, Kq, Ksp, KLPRS, I don't know, K everything. So what's the relationship between delta G of the reaction and K? Well, here's a problem we're going to do, but let's think about this first. Okay, we have delta G, okay, and what we're trying to usually look for delta G is something spontaneous or not. Now remember, if delta G is a negative sign, this is spontaneous. So I'm going to put this over here. And I should actually put it over here. Put delta G, and then I'm going to put K right here. Get rid of this. So delta G is negative. This is spontaneous. Okay? If delta G is positive, this is going to be non-spontaneous. Okay? But what about K? Okay, think about K. When we say something is spontaneous, that means we're going to make a lot of product. We're going to make a lot of product, okay? Because we have this reaction, we'll say A going to B. If it's spontaneous, that means B is really stable because everything's moving towards greater stability. So if this is really stable, we're going to make a lot of B, okay, a lot of product, okay, because it wants to go on its own, okay? That's what spontaneous means. A wants to turn into B on its own. Okay, so that means we've made a lot of products. So let's look in terms of K. K equals to our products over our reactants. So what does this tell us about K? Well, when we make a lot of products, so our products have increased, that means K has increased. So basically anything greater than 1, if K is greater than 1, that means you've made a lot of product. That means you have a large K. And that means you have a negative delta G. Okay, so basically, if K is large, and we're going to define large as greater than 1, so K is greater than 1. So basically, it's a positive exponent. So if you have a large K, we've done this before, if we have a large K, that means you've made a lot of product. Okay, and if you made a lot of product, that means it's spontaneous. Okay, but if K is small, so a small K, that means, put product over reactant. We didn't make a lot of product, okay? We're looking at A going to B. Okay, it mainly stayed right here. That means the reaction didn't really go, so it's not spontaneous. Okay, so that means it stayed as reactant. Okay, so that means we have a small K. So K is small, and we're going to define that as less than 1. Okay, so that's how delta G and K are related to each other, because K kind of basically tells you, did you make a lot of products or not? If you made a lot of products, that means it's spontaneous because it's really reactive, so delta G is negative. And the reverse for if it's small. So let's look at this problem right here. And here it is. It says use the tabulated free energies of formation to calculate the equilibrium constant at 298 K for the following reaction. Oh, and I should probably give you this. Here is the formula. So delta G of the reaction, this has a degree sign, so this is standard state, equals to minus RT natural log of K. R is still 8.314. T is your temperature, and then K we're trying to solve for. Okay, so here's our formula to relate delta G to K. Delta G of the reaction equals to, now all of a sudden I cannot remember the formula. Yeah, minus RT ln K. Minus RT natural log of K. R is going to be 8.314 joules mole Kelvin. Temperature, in this case it says it's at 298. And delta G I don't, oh, and let me put the degree sign. Delta G I don't actually have yet, but I know I can find these. They want you to look up the tabulated values. I mean, look up at the chart and figure it out. So that means do the product minus the reactant. So let's see, I have N2O4, looking at the reaction right here, and NO2. Okay, the number for N2O4 is 99.8. Oh, and these are in kilojoules. And NO2 is 51.3, also in kilojoules. So let's see. My product is NO2, and it has a coefficient of 2. So I'm going to do 2 times 51.3. So when I do that, 2 times 51.3, oops, 0.3, I get 102.6 kilojoules. And then my reactant is N2O4, which is 99.8. 99.8. So if I do my products minus my reactant, which is going to be 102.6, then minus my reactant, which is 99.8, I get delta G is 2.8 kilojoules per mole. Okay, so this is my delta G number right here. Now let's plug everything into the reaction because I have my R. R is always a constant. I have my temperature, and now I have delta G once I solve for it. So now let's get my K value. So let's look here. Delta G is a positive number. Do you see here? So first of all, is this reaction spontaneous or non-spontaneous? Non-spontaneous. Okay, so let's predict some stuff that we would know about K. Well, if this is non-spontaneous, will K be large or small? Well, if it's non-spontaneous, that means we didn't make a lot of product. So we're going to predict K equals to small. So K is going to be less than 1. Okay, so let's make sure that's what we should get. So we have delta G is 2.8. Oh, and this is in kilojoules. Remember this, kilojoules, and this is in joules. Okay, so I have a kilojoule right here for my delta G. Let's convert that to joules. So there are 1 kilojoule equals to 1,000 joules. So 2.8 times 10 to the third joules. Okay, now let's plug them in. We use a different color now. This green color, I guess. So delta G of the reaction is, oh, that looks too similar. Let's use orange. Let's put it in over here. So we're plugging everything in here. So we have delta G of the reaction is 2.8 times 10 to the third equals to minus R, 8.314, times our temperature, which is 298, and then I'm running out of room, and this is going to be all multiplied by natural log of K. Okay, so let's do this. Let's first do 8.314 times 298. Okay, so hold on. That'll be 2.8 times 10 to the third equals to, okay, 8.314 times 298. So here I'm going to get negative 2,477.6 natural log of K. Now let's bring this over and divide. So 2.8 times 10 to the third divided by 2,477.6. That might be a negative. So I'm going to get negative 1.13 equals to natural log of K. Now to get rid of natural log here, you're going to raise, or you're going to do E. You have to do E. So basically, on the calculator, to get rid of natural log, you had to put in, and this is natural log, second natural log. That's what you're going to, second natural log. okay, which is your e to the x number. So e to the x. So e to the x, ex is what you're trying to raise it to. In this case, natural log gets rid of it. So e to the x, so e gets rid of natural log there. Okay, and what is your x? Because you know you have e to the x. X will just be this value right here. So you're going to do second natural log. That's going to be raised to the negative 1.13. And I get k equals to 0.32. Is k less than 1? Yes. And so we predicted correct. All right, so it's just plug in your R and your T value. Usually you're going to have to calculate delta G, doing your products minus your reactants, and plug that in to solve for K. So I do want to kind of quickly go over, like, when do we do each type of problem? Okay, so you can do delta G at standard state. Okay, first you could do the calculated delta G of standard state. And this is delta G of the chart. So from the chart, and it'll say calculate delta G at standard state. So again, you're going to see that degree sign there using tabulated values. It'll say something about using tabulated values from the chart or something like that, okay? And that's where you're going to do, your products minus your reactants of delta G. So that's one way. Another way they could give it to you is you have to use delta G equals to delta H minus T delta S. And you'd have to calculate delta H and calculate delta S using, the chart. And then plug those in to this formula here. Okay, and they would say something about delta H and delta S. The third way would be Hess's law. And that's when you multiply your delta G by a number, or you flip it, all of those. Okay, so that's when to use those here. If it's at non-standard state, then remember the formula then is delta G of the reaction equals delta G of the reaction at standard state, okay, plus R, wait, did I do that right? Yeah, RT natural log of Q. Okay, so you would just plug that into there. And then if you're trying to relate it, so this is at non-standard state, and so you would have no degree sign right here. And then if you're trying to relate delta G to K, you have delta G of the reaction, standard state, equals to minus RT natural log of K. So it really just, again, depends on what they're asking, which formula and how you calculate it.